Hi folks, welcome to the concept roundup for Math AASL. We're looking at bivariate stats, so correlation, linear regression, and also a little bit on piecewise functions. In the video description below, you can find a blank copy of the notes, and you can also find at the end of this video some review questions that you could do from the Oxford textbook. This is Chapter 7 in the Oxford text, and here we go. So correlation, or Pearson's correlation coefficient, is a measure of the strength of the linear relationship between two variables. So if it's positive, that means as one variable increases, so does the other. And if it's a strong value, that means something close to 1, then it's going to be very linear looking. So a strong positive correlation might look like this. It's not perfectly linear, but it's pretty darn close. So R can take values between 1 and -1. So right here, this might be like R of 0.96 or so. It's really good. Strong negative, that would mean as one variable increases, the other decreases. So again, if it's strong, it's quite linear. There we go. That might be an R of -0.96. If you have a zero correlation, then there's no real corresponding relationship between the x and the y values. It would kind of look randomly distributed. You can't get a real pattern out of them. So that would be R is 0. Now, what does it mean to have a medium positive? Well, that means it's still positive, so as one increases, so does the other. But it's not exactly linear looking. There's a trend, but it's not perfect. Okay, so that might be an R of, I don't know, 0.5 or so. And if we have a weak correlation, then, I mean, it's sort of there, that linear relationship. But maybe we have some outliers here. That would be pretty weak right there. So that might be an R of negative, I don't know, 0.2. If you don't have a strong linear relationship between two variables, it probably doesn't make a whole lot of point to make a line of best fit or a linear regression. Okay, so if we want to calculate R on a TI-84 plus, we enter the data in lists 1 and 2, and we use lin-reg. If it doesn't work, you may need to turn on stat diagnostics, which is under catalog, and there's just a whole bunch of things that you can choose. One of them says diagnostics on, and you just hit enter twice. Lin-reg is under stats, which is also where the lists are, and then you'd press over, and lin-reg is 4. Now I'm doing this on an iPad, so my TI-84 emulator isn't perfect. It's leaving out a couple little things, but it's mostly good here. So here I've got the age of 6 vehicles shown along with their odometer readings, the vehicle age in years, and the odometer reading in thousands of kilometers. So if you see a 62 here for Y, it means 62,000 kilometers on the odometer, okay, which counts how many kilometers the car or vehicle has been driven. And those two things are probably somewhat related to each other, though we all know of cases of cars that are not that old that get driven a lot, and cars that are very old and don't get driven that much. What we want to do is write down the correlation coefficient. So I'm going to head to the TI-84 and put in this data. Here I am on the TI-84. I press Stat. I press Enter for Edit the lists. And I've already put these in. In L1, I put all my X values in. In L2, I put all the corresponding Y values in. Now I'm going to quit, which is second mode. And I'm going to do that linear regression. So it's stat. I press over, so it now says calc. And on your calculator, you'll have more options than this. On my emulator, it's only got 1 variable stats, 2 variable stats. But luckily, it does have the linear regression AX plus B. And we might as well just use that one. So linear regression AX plus B, it'll ask us, what's our X list? It should generally be L1. What's our Y list? It's L2. And you can decide to store it somewhere. We won't necessarily go through that right now because the IB often asks us to write down the regression equation so that we get around some sig fig issues. So I'm just going to press enter, And for mine, it came up with the A and B values. What I really care about, though, is this R value of 817. So that's the correlation coefficient. It's pretty strong, and it's positive. That makes sense. As the number of years that the car has been around increases, the odometer reading generally increases, though it's not a perfect correlation. So there's that correlation coefficient written in. We might also want to look at these points plotted on a graph, and you can see that they do look somewhat linear, though perhaps not perfectly so. So here's the actual data values, and here we have odometer reading versus age. That brings us to linear regression. So a y on x linear regression, or an equation of the form y equals ax plus b, it's a line of best fit for the data. It's generated by minimizing the square of the vertical distance between the line and the points. And so this is the most common linear regression, is the y on x one, and it's what you would use to predict y values. The linear regression always passes through the mean point. So here we've got the same question. If we wanted to find the coordinates of a mean point, the mean of all our x values would just be add them up and divide by the number of values we have, which is 6. And that's going to give us 7.33 roughly. The y values, we can do the same thing. We can also use the one variable stats on our calculator to find these means. So I can show the process here, or I could just go and use the calculator. Divided by 6, because there are 6 pieces of data. And that's about 150. Again, we're going to 3 sig figs. So the coordinates of the mean point are 7.33, 150. Let's go and take a look at the graph of all this stuff and maybe plot that point. So 7 1/3 and 150 is right here. 7.33, 150. If I were to make a line of best fit through all this, I probably would go through that mean point. I'm sort of splitting the difference on the distance between the points and the line. That looks like a good by hand line of best fit. And the mean point gives us something to anchor it around. Now, we can also get the calculator to generate a linear regression, which means a computationally derived line of best fit in the form y equals ax plus b. And we actually already did it. When we had the calculator generate the r value, it also gave us this line that says y equals ax plus b, and it tells us that the a value is 14.6 to 3 sig figs, and the b value is 43.5. So that apparently is the linear regression. The IB will often ask you to write it down so that when you use your linear regression later on, then you're using it to this many significant figures. Now, slope measures rate of change. Slope is change in y over change in x. So in this context, we know that slope is 14.6, or we might call it gradient. Now, what is this measured in? The y's on our graph were 1,000 kilometers, so 14.6 thousand kilometers per, what were the x's? The x's were years. So the slope in this case means that the odometer reading increases at a rate of 14.6 thousand kilometers per year. Another way to interpret that would be to say that on average, the car is driven 14.6 thousand kilometers per year from this sample using this regression. So the slope of your regression has meaning. It's a rate of change. Rate of change. The y-intercept also has meaning. So the y-intercept on any line tells us what happens when x is 0. So for us, we had 43.5. Y-intercept is 43.5, and we know that means 1,000 kilometers. And that's happening when x equals 0. So in other words, what it's saying is a 0-year-old vehicle will have an odometer reading of 43.5 thousand kilometers. Now, if you're looking at that and saying that doesn't make sense, that's good. That seems really weird. It's the reading that we get, or the result that we get from this linear regression, but it doesn't seem to make a whole lot of sense in context. And we'll talk about why that is in just a second. That is the meaning of that y-intercept in this situation. If we look at this linear regression, here it is around those points. You can see its slope is going to be about 14.6 thousand kilometers per year. And right here, there's that y-intercept. And it is telling us that at age 0, we can expect an odometer reading of 43.5 thousand kilometers, which is really weird. Okay, that brings us to interpolation and extrapolation. These are techniques that require us to use our regression to make predictions or estimates. Okay, so it won't necessarily tell us exactly what's going to happen with a particular vehicle, but in general, sort of what we can expect based on the data that we have. Interpolation means finding values that are between the extremes of our data. So we saw cars that were, or vehicles that were between 3 and 12 years old. We can probably make okay estimates of what's going on for vehicles between those ages. Generally, interpolation is okay. Extrapolation is when we make estimates that are beyond the extremes of our data. So if we were to estimate what's going on for a 0-year-old car, things seem to get pretty weird. Or if we were to talk about a 100-year-old car, I mean, obviously, this model probably doesn't keep working. Extrapolation is something that should be done with care. If you want to have just a hard and fast rule for it, the IB is saying it's not okay. So that's why this value over here, 43.5 thousand kilometers for a 0-year-old car, is not something that we put a whole lot of stock in. So now that we have the regression equation, we can use it to actually predict some values. So it says use your regression to predict the following if appropriate. The odometer reading on a 9-year-old vehicle. So remember, the age is x, so we have this regression equation up here, 14.6x plus 43.5. What if we put in 9 for x? Well, then we get an estimate of the odometer reading on a 9-year-old vehicle. Now, if I run that through on my calculator, I'm going to get about 175, which remember here means 175,000 kilometers. Okay, that seems like a reasonable estimate for the odometer reading on a 9-year-old car, depending on how much you drive. The odometer reading on a 20-year-old vehicle. Now, let's think. That would be extrapolation. We only have data that runs up to 12-year-old cars. To go for a 20-year-old vehicle seems like a stretch. So no, we're not going to do this. Not appropriate because it's extrapolation. Could we do it for a 100-year-old car? No, that would be absolutely ridiculous. So extrapolation. All right, lastly, the age of a vehicle with an odometer reading of 120,000 kilometers. So this seems like it would be reasonable, but there's actually a rule that we have to follow that says we can't predict the independent variable using our standard regression. So can't predict x from y using a y on x regression, or a typical regression. There is a technique that we can use that's okay, and that involves just switching around the roles of the variables. Now you might think, well, isn't that just the same as subbing in different values? But the technique ends up being a little bit different. If we want to predict x values, we need to do an x on y regression, which is going to give us this weird equation, x equals ay plus b. Now again, that just seems like a sleight of hand, but the technique ends up being a little bit different and a lot less common. It involves minimizing the square of the horizontal distance between the line and the points. And remember, for our other regression, it was the vertical distance that we minimized. Your calculator does not want to do that. But you can trick your calculator into performing this kind of regression just by switching list 1 and 2 in the regression. So that's what we're going to do here. We're going to do one of these x on y regressions so that we can actually answer the question that was just asked, the age of a vehicle with an odometer reading of 120,000 kilometers. So in order to do the x on y regression, we're going to do a lot of similar things that we did before. I'm going to go to Stat. I'm going to make sure that my information's in there. I can leave them in list 1 and list 2, respectively, for x and y. And now I'm going to press second mode to quit. I'll press Stat again and go over to Calc, so I press to the right. And once again, I'll go lin reg ax plus b. The thing that's going to change this time is that I'm going to tell it that the x list is L2. So I'm just switching the variables for the calculator because it will never do what I want it to directly. So I'm going to tell it that I'm going L2 for my, quote, x list. I'm switching them up, which means I'm going to switch them up when I write the answer too. So I have L2 and L1. Seems weird, and that's because we're doing it the other way around. I press enter. Notice the correlation doesn't change, but the equation sure does. It's going to be the a value is 0.0458 and the b value is 0.443. And it says y equals ax plus b, but we switched those lists around. So we're actually going to get x equals ay plus b. Using all that information, here comes the regression equation. X equals 0.0458, y this time, plus 0.443. Once I know that, I can sub in 120 for y. So I've done this slightly different regression, and I'm going to get x equals 0.0458 times 120, which was my y, plus 0.443. And when I run that through, I'll get about 5.94, which seems kind of reasonable. 5.94 years old. That's how old we can assume the car is. You'd get a different answer by subbing in 120 into the other regression equation. The last part of the chapter has to do with piecewise functions, and these are functions that have different definitions depending on which chunk of the domain you're dealing with. So we want to be aware of general shape, the locations where it's sort of hands off from one definition to the next, which I like to call split points, and whether the split points should have open or closed dots. If they're included, they should be closed. If they're not included, then they should be open. So here's a weird function. It's got this first section here where it's a parabola. It's a basic parabola until x equals 0. Now, what happens if I put 0 into this? Okay, if I put it in 0, I get 0 squared, which is 0. That's the end of its definition as a parabola. And so up until x equals 0, it looks like a parabola. Notice that there's this less than or equal to, so that means it's included or closed dot. I'm going to go ahead and start to graph this. So I'm working from left to right. It's going to be parabolic in nature right up until I hit x is 0, and there's my closed dot. After that, it turns into a line, and I'm going to change the color, even though it's still the same function, just to try and show you how we have different definitions over different little chunks. Okay, so it's a line, and it has sort of a starting split point at 0, something, and an ending split point at 2, something. If I put 0 into this, I'd get negative 2 times 0 plus 1, or I'd get 1. That's sort of where it starts being a line. And notice here that it is not included, so I'm going to have an open dot. Okay, it doesn't have an equal sign on that less than symbol. So here's that open dot. And now it goes to the end of its sort of linear chunk. If I put in 2 into this, I'll get negative 2 times 2, which is negative 4, plus 1 is negative 3. And that's going to be a closed dot, because at this part, at the ending bit of the linear chunk, it's included. So closed dot, or filled in dot. Okay, so 2, negative 3 gets a filled in dot. And in between those, we've got a linear chunk. Lastly, at the very end, and again I'll change colors even though it's all one function, it becomes the horizontal line at -3. Y equals -3. Okay, so as a split point, I guess it's 2. Y is always -3. Notice here it's not included, so open dot. That open dot is already filled in, though. So it was filled in with green. I'm showing it as an open dot. That's how I end up generating the rest of the graph. I'm going to go back and do this all in black because it's all one function. So in the very end, that one's closed in. This is open. Goes through here. This is closed, so it doesn't matter if I draw it as open afterwards. It's already been filled in. And there's my graph. Piecewise functions are useful for graphs that have different definitions over different segments. Overtime pay is a good example. Tax brackets are a good example. That brings us to the end of Chapter 7, or Bivariate Statistics, with little piecewise functions to throw in. If you want some practice material from the Oxford text, you could do the chapter review that's on page 344 to 349. There's some basics, some more advanced, and a challenge one. I hope you found this useful, and good luck with the material.